another film clip. Okay, so just as opening, this is March 8th, and this is ECE 3030. This is ostensibly a makeup class, but we're going to use this as a review for next Monday's midterm. So let me start off with one set of things. I don't know how well this shows up on the recording, but this is our Carmen web page, and I just want to highlight to you the different segments where we left off on the first midterm and where this midterm is going to be covering. So midterm number 1 covered the segment 1 bonding crystals epitaxy, so that's not in play here. Segment number 2 is doping diffusion, not in play here. That's midterm 1 material. Then this one is mixed. We had a portion on segment 3 called oxidation. That was on midterm 1, but where the quantum mechanics start, that's where this midterm starts. So that includes fundamentals of quantum mechanics, like the design problem that you're doing right now actually kind of plays into that, and the origin of bandgap. That's a high priority. Origin of why do we have a semiconductor bandgap? Where does that come from? How does that mystery drop out? Understand that. Segment 4, carrier statistics. You know, the Fermi-Dirac statistics. Fermi-Dirac transport. That's all in play. Segment 4B was like a one-page thing, a handwritten one that just kind of augmented that. That was related to density of states, and I was trying to just declare how you could park cars, and you could have different geometries essentially to the density of states. I'll be trying to drill through this very quickly right now, and then I'll open up for questions. Segment 4C, charge motion. So once you put charge into this system, in other words, once you put in free holes and free electrons, what makes them move around? Well, the two primary things, of course, are drift and diffusion. So just understand that. And then you drill down to the 432 segments, because now we've bridged into 432, and you have the p-n junctions, the formation of a p-n junction. Now, where I'm going to truncate it is that the biasing of a p-n junction won't be, because I think that's about where we were starting on Monday, and I like to give, thematically, I like to give you 1 week to digest everything, including a weekend, before I hit you with the midterm. So around Monday, which was 1 week before the next Monday's midterm, we had completely finished talking about formation of the p-n junction, and we hadn't quite finished talking about biasing, so I probably won't go there. I think there's enough material for me to test you on. It does leave a number of things left for us just to finish out the year. Of course, we're going to have to talk about these p-n diode applications, and then field effect transistors and bipolar transistors. That's what's coming between now and the close of classes. Okay, so let's go through some of this. I think this is all on the desktop now. Let me order it. This is 432 segment 2, and this is segment 3, and segment 4, 4B, 4C. Okay, so then I think these are roughly in order. And this is bandgap. Of course, bandgap's very important. Oops. So these are, I think, the ones we're having to talk about. So let's start off with the first one. Okay, this was the big picture, and then oxidation, which was the first midterm. But then here we're kind of, in some sense, this is a review of quantum mechanics that you may have had in physics. So that's why I started off slowly, talking about tunneling through a barrier and how that attenuates. You sort of have a plane wave function, and it attenuates, decays exponentially, and if it hasn't been decayed to the point it extinguishes, and it's a finite amplitude at the end of the barrier, then the plane wave can continue on the other side. So this is quantum mechanical tunneling, which we were just talking about in the context of yesterday's makeup lecture on Zener tunneling, which Sarah, by the way, should be posting momentarily. She's making, I think right now she's creating a YouTube channel for me, so be look for that pretty soon. And here you can see some waveforms as it interferes with different boundary conditions. And hopefully you're starting to learn that I can create these boundary conditions by epitaxially growing different materials that are low band gap, large band gap, and so forth. So I can make all these artificial things I can synthesize in the lab by systematically epitaxially growing on a substrate of a variety of materials. And of course, this is the sandbox in which we play. These are some of the 3-5 materials that we can deposit with different range of lattice constants and band gaps. And that's where, you know, this quantum well problem that I have you designing. Yeah, here's maybe the more colorful version of it, where you have this traditional 3-5s. Some of these are 2-6s, which are less used, less represented in the field. The 3-5s dominate, and the new player on the block is the nitrides. This data point, by the way, is wrong. It should be actually down here. This is an older version. If anybody ever finds the more updated one, I'd love to get a copy. Feel free to email me. I'd really appreciate that. And so then what I started with in the lectures, and kind of where the midterm will be covering, is starting from your old freshman chemistry. And so this is, you know, the energy levels of a single discrete atom. And so you can see this is represented where the nucleus is, where the nucleus of the atom is. And then you have these boundary conditions where you have different bound states, representative of 1s, 2s, 2p, and so forth. And then the model is what happens. Remember, the story I was using was this Gedanken experiment. I have a whole bag out in outer space of Avogadro's number of silicon atoms. And I start to squeeze them together so that now the different atoms start to come closer and closer together, and they start to influence and sense each other's presence. And it's basically an extrapolation of things you've already learned, Pauli exclusion principle, that dictates that if I have a spin up and spin down electron over here in this atom, and I have a spin up and spin down electron over in this atom, they cannot, once they sense each other's presence, they cannot sit at the same quantum number, right? Pauli exclusion principle says it has to be unique. So therefore, there's a splitting of the levels, and I kind of gave the analogy in class that it was akin to plate tectonics, where you have, you know, the Pacific Rim hitting the Asian, and the Himalayas are growing as a result of the two plates hitting each other. And so as a result, that's kind of what this shows. Let me blow this up because this is the important one. This is one of the, you know, you can almost guarantee there's going to be a question related to somehow to this on the exam, because band gap is so fundamental. And so here's your bag of gas, you know, a bunch of discrete energy levels, 1s, 2s, 2p. But as you scrunch it, as you push it together, and it experiences each other, there's that plate tectonics, all that splitting. This is what I was trying to do, is shape this in and represent to you that this is not empty space. This is actually a whole myriad of closely spaced energy levels, so closely spaced that it, for all intents and purposes, smears into an entire continuous band. And it turns out that as you push this more and more, and this is the preferred interatomic distance. This is why I hammered that home in midterm 1. What is the preferred interatomic distance inside a crystal? Well, this is where the crystal will solidify. I truncated this a little bit, but here you can see this is the diamond lattice. This is the interatomic spacing in a diamond lattice. And at that particular distance between the atoms, so once it's crystallized, then this is the band of energy levels, and this is the band of energy levels. And it's split in such a way that I have 4 n states. I have 4 states per atom, and then I'm saying in this Gedanken experiment I have something like Avogadro's number of them. And so I have 4 n states per atom and 4 n states up here. So it's a 50-50 mix. And then you remember our density of states. If I can jump over to, I think this one. Nope, not that one. Yeah. So I was trying to say this is like parking. This is the segment 4B, by the way, from the 331. I was saying I could have density of states. I could have a triangle where the apex is pyramidal and sticking up. I could have a rectangle. I could have something like this. Okay, so this is depending upon how the density of states is represented as it's going deeper into the bands. And I think I've been trying to present to you that it actually is the density of states gets larger as you go deeper into the band. So actually, this is actually more like what really happens in real life. You have only a few parking spaces at the edge, and then it actually goes up as the square root of energy. And this is linear. But you can park more cars deeper, towards the top, actually. And so, but as I fill that up, oops, I missed, I want to go back to this one. As I fill that up, what I started with was a 2s state and a 2p state. And if I'm taking a group 4 element, in this case I think it was carbon, but let's use silicon. Silicon is a group 4 alloy, group 4 elemental material, so therefore it has 2 electrons in the 2s state, and it has 2 electrons in the 2p state. So each silicon atom has 4 valence electrons. So once I've smushed it and pushed it into this continuous valence band and continuous conduction band, now I need to, in this density of states, find places to put the 4 electrons per atom. Well, I'm going to start at the bottom. That's what Pauli exclusion principle teaches us. And I'm going to load it up, and by the time I get to the top of the valence band, I've run out of electrons. Because this has 4 states per atom, I have 4 electrons per atom, so this is completely filled. So remember the argument, it's housed in the video that needs to be posted on YouTube from yesterday's makeup lecture. When we were talking about Zener tunneling, and I was saying that we had all these carriers deeper and deeper in the valence band, now you can see where this is coming from. These are the electrons I was referring to about Zener tunneling. These are the ones that are ready to march and tunnel. But we run out of carriers, so the conduction band is normally empty. Thus, remember why we've agonized over doping, over acceptors, over donors, over free electrons, over free holes. Because normally this is fairly uninteresting, because this is all filled with electrons, so nothing's going to move. And this is all empty, nothing's going to move. So there's actually no net current transport, right? So, if there's one electron exchanges with another electron, the net effect is 0. So until I open up some free holes there, or I open up some free electrons there, there's no net effect. So I need the doping, I need the acceptors, I need the donors, and I need them to be ionized and liberate their charge. So this is the origin of the band gap. Which is also explained here. This is a different version of it from a different textbook. This is showing you, again, another version of just taking 2 of those atoms and smushing them together, and they split into an anti-bonding and bonding. And this is exaggerated for the cartoon's sake. It's actually, they're very, very infinitesimally split from each other. And it's sort of like having a wave function that is sort of the sine wave, and sort of the absolute value of it or so. And then here's another representation, kind of the Kronig penny model, that you make a linear array of these atoms, and these atoms, again, the nuclei are positioned here. That this is going to merge into a continuous band, so charge can move through the crystal in this energy state. So I know this is a source of confusion because a few people will talk to me offline. recognize many times we're talking in this class about in the energy world, an energy band diagram, that in energy, sometimes we talk about it in the physical world, of it physically an electron going through the physical crystal. And sometimes we even talk about things in the temporal world, when we think about something kind of existing for so many tau lifetimes before it's reabsorbed. So try and keep all those different worlds straight. There's the temporal world, there's the real spatial world, and then there's the energy. So this means that the carriers can move through an energy. Now, it may be distributed through the real space crystal and in some random way, but and so here's kind of the showing the wave function, and this is kind of a way of showing how a free particle, the old physics, throw a ball up, goes through a parabola, comes back down. So the kinetic energy of a ball is 1/2 mv squared, right? So this is an electron going through free space. It's 1/2 mv squared, but if we rewrite it, if you remember in momentum, we write it as p squared, p being mass times velocity, p squared over 2m. So 2 being the 1/2 that we originally had. So this is p squared. Now we're going to convert to a wave vector k. So that's a vector. So it's telling me which direction I'm going through the crystal. Remember, the band structure, this is the origin of the band structure, is crystallographic direction dependent. Because if you look at the crystal, any of those models I passed around, and they're I think they're still in my office still if you want to take a look at them. As you go through the crystal, depending on which direction you go, you see a different interatomic spacing. If I go through diagonally, I'm going to see maybe the hypotenuse of a triangle, and it's going to be a little bit longer. So that's represented by these different directions. And when you make that periodic crystal, it's basically like you're doing a Fourier series expansion of the crystal. And certain Fourier components are allowed, and some are destructively interfered with as it goes through the chronic penny. As you go down, now this is actually not it, but you can imagine that going through the crystal, if these are the different atoms, right, I would probably have where the wave function would be peaking right where the atom is, because that's where the valence are. So I'd have certain harmonics of the wave function that would be expressed, as harmonics of these. And anything that was asymmetric, where it would probably be destructively interfered traveling through that crystal. That's basically what it is. If you kind of have some working knowledge of Fourier series, Fourier expansions, that's kind of why it opens up these gaps. And so there's allowed and disallowed states. It's sort of saying that there's certain Fourier series components that are allowed and some that are not. And so then that's what this shows. It shows that I no longer have the parabolic p squared over 2m, but it's now fractionated into these bands. Then we do our funky little origami. We fold space in on itself. This is K space. This is reciprocal space. So actually, I guess there's 4 things you gotta to keep track of. This is reciprocal space. The K space. And so you do the origami and it opens up. But again, don't forget, keep the eye on the ball. It's really that there's a density of states. These are representative at various energy levels. And as I fill in my 4n electrons, that same diagram we just talked about is in play. I fill up my 4n electrons. I'm filling that band. I'm filling this band. And I actually run out of carriers. And this becomes the edge of my valence band. Because what's interesting, you can see there's multiple gaps here. Which one of them is the band gap we always harp about? The band gap we always harp about is the one that is at the boundary edge of where carriers are, valence band, and where carriers are not, conduction band, unless we doped it or excited it with a photon, or gave it some heat, or did something to ionize and perturb the equilibrium condition. But normally this is the valence band, normally it's filled. This is the conduction band, normally empty. So then you can see how I have to have, because this is K-space, right? The X is now this K-space, this momentum vector, that I can have direct band gap. These are very efficient light emitters. These are your LEDs, your laser diodes. This is indirect band gap, which is actually silicon and germanium, your workhorses for electronics, and that's why you don't have a silicon laser. Yeah, in fact, here's more representative. This is the actual, these are the two main biggies. This is the, of the elemental semiconductors, silicon, this is the most dominant one. And you can see that's where the holes go, that's where the electrons go. And this is the most dominant 3,5. This is gallium arsenide, one of the most oldest studied 3,5 compounds. And here's where the electrons go, there's where the holes. So I don't need to involve a phonon for momentum conservation for an electron and a hole to get together. So it very efficiently, as an electron falls down, it can release a photon, or it can absorb a photon by absorbing it, and that'll kick an electron up there. But its conservation of energy is the net effect. Conservation of energy, conservation of momentum. And here's another textbook version, a little more detailed. Here's another version. Here's another version showing the aluminum gallium arsenide ternary alloy. As you put more aluminum in, it's showing you that it's only the gamma, which is the direct band gap. The terminology, you might not have fully absorbed that, but gamma is representative of direct band gap. It's direct band gap until these X or L valleys, the indirect valleys, cross, which is right here. So it's around a little beyond 30%. So this actually puts a boundary condition of how much aluminum I can put into aluminum gallium arsenide and still get light out. So it turns out that's actually a rate limiting step, because aluminum gallium arsenide at 0% aluminum, I got pure gallium arsenide. That's an LED that emits at 850 nanometers. That's probably this remote control here. It's talking to that camera. I didn't realize it was on the wire. But there's probably a gallium arsenide LED in there. And it emits at 850 nanometers. And since your eye only goes to a little beyond 750, your eye is unable to see it. So 850, but then as you put more and more aluminum, the band gap goes up. Eventually you get red. But I can't push this all the way to orange. Remember, Roy G. Biv. I can't get this to orange because it becomes indirect band gap before it becomes orange. So red LEDs, I can almost guarantee you, are aluminum gallium arsenide with a ratio of aluminum below 30%. Yeah, this is actually from that Simon Z, the big thick one that I said we use for graduate school. This is showing the germanium as well, silicon gallium arsenide, the same. So that's the full band structure, not to be confused with band diagrams. And the way I described band diagrams is the band diagram is representative of the extrema of each of the bands. So I only want to know where the lowest energy is in the conduction band and the lowest energy is in the valence band. So the lowest energy in the conduction band is down, because electrons fall down like bowling balls. So that is the conduction band minimum. So when I make a band diagram, the things we've been studying in class now, when we talk p-n junctions and the band diagrams, and there's band bending, what we have done, this needs to be revisited, it's like I pull a thread out of the sweater of the band structure, and I'm representing that point in K space And that's the energy level that is being extrapolated into the band diagram. And as you're starting to see, the band diagram now will be as a function of X. It's not going to be because I'm going to have epitaxially grown or diffused in or so forth. So it's a cross-sectional view of the bands as I go through the device, as I do a cross-section through the device. But it's representative of that point in K-space, an EK diagram. And then I'm taking the extrema, the lowest energy in the valence band, which of holes, you have to stand on your head. Holes are like air bubbles. Their lowest energy is actually up. So I'm plucking a thread out of the EK diagram right at the band extrema. So I tend to prefer the nomenclature band extrema because if I say minimum, then you might misconstrue and think I got to pick somewhere down here in the valence band, but it's actually there. Question?
So we're almost looking at it from the side because we're looking at the minimum.
You're looking at the
minimum,
the two extrema.
And that's where we get our band diagram. So
That's where you
kind
get
of flip it on its side, and we're looking at the minimum and the
Yes,
maximum.
it's like pulling a thread out. Yeah. So then you can see, now that becomes the framework as to then how can I put charge in. And of course, nothing interesting happens until I put charge in. And so this is representative of an undoped semiconductor. Technically, this is a function of X, but it's just a dumb slab, so it's kind of boring. And so this is not 0 Kelvin, because obviously I've had a few carriers that have ionized, creating a free hole and a free electron. And recognize the diagram has hopefully carefully controlled this so that the electrons and holes are in a 1-to-1 ratio. So it's still intrinsic. In other words, it doesn't have a electron-rich character. It's not N-type. It does not have a hole-rich character or P-type. It's technically neutral. And so I have equal numbers of free electrons and equal numbers of free holes. But I can start to get something interesting now that you're starting to see in the lectures about p-n junctions. This is when I start to have some fun, because I put a donor level in, which, remember from the midterm, first midterm, was a substitutional donor dopant. In our classic case, it's a phosphorus atom with 5 valence electrons into a silicon crystal, which has 4 valence electrons, 4 covalent bonds. So that 5th electron is easily liberated, probably at just 50 Kelvin, is enough to cause that electron to be pulled away, because this energy level is very, very modest. And so I have free electrons. With this diagram, what I've always harped about in lecture is, don't forget that that donor is ionized. It's a plus charge. That's the origin of our depletion region and the ionized charge in the electric field in our p-n junctions. Really doesn't need to be said. Same thing with acceptors, so they create free holes. And then this is the classic Fermi-Dirac statistics, that carriers are smeared over the energy levels as the temperature is raised. So you can imagine that the KT, the energy, as I'm adding thermal energy, that some carriers that normally sit at these lower energy levels, this is supposed to be energy. Maybe I need to lower the magnification a little bit. There. So the x-axis is now energy. And so these are the lower energies. So some of these jump up to the higher energies. Now I prefer to see this, some of these other graphs, they turn this on its side, because I'm usually thinking energy goes up. And so I like to do this. This makes more sense to me. This is the Fermi level. Fermi levels, the probability of occupancy is 50%. But I hate that mathematical definition because it doesn't tell you the true story. The true story is that I have an equal number of electrons available above as I have holes below. So every one of these electrons that were here has ostensibly jumped up to a higher level. And therefore the Fermi level is a watermark level of where the carriers, average carriers are residing. And so then once you put the whole thing together, and you have that density of states I was referring to earlier. So it's going up as a square root of energy, deeper into the conduction band, square root of energy deeper into the valence band. This is where I can park my cars. This tells me where the cars are, where they want to, how many need to be parked. And then the product of these becomes, this is where the actual cars are. So I got some parked down here, down into the sub-basement, and I got some parked up towards the roof, and then the office space in the middle where no one's allowed to park. The forbidden band gap. And so then these are candidate dopants that go in. Obviously the donors are the ones towards the conduction band, the acceptors are towards the valence band. If you really want to see, this is from that Simon Z, the big thick book. This shows you almost the whole periodic table being dumped in there and all the candidates. Yes,
I
question?
think donors are near the top.
Donors are always near the top.
Okay.
Yeah. And this is just another representation. And there's another representation showing you that this is intrinsic. This is an N-type material, so the Fermi level, the watermark level's gone up, and as a result, the product of these two results in I have a dominance of electrons up here and a suppression of the holes below its normal level. And what controls these? What controls those is nothing more than Ni squared equals N times P. So as N grows, it grows at the expense of the P. This is the majority carrier, that's the minority carrier. That's the end of segment 3. So there's a lot of fundamentals there that I'm hopefully now actually going back through the review, and as we're doing the PN junction study now, I hope you're starting to see now where this is coming from. I think we did this a few weeks ago, and so that was segment 3. Let's do segment 4. So again, this is that thermal yardstick. This is where I get that discussion, where I get this Gaussian distribution, and KT's right here. This is kind of cut off. Yeah. This is the KT. So this is the average energy carrier has in the system. But it's a bell curve, kind of like this class. We have some really good performers, and we have some really weak performers. And so the Usain Bolt's up here, and one of them's in this class right now, is way up here. And this is the one that can jump the forbidden band gap. So if they get enough energy, this is the energy. If that energy exceeds this, then it has enough energy to jump gallium arsenide band gap, which is 1.4 electron volts. If I'm a little bit less, I can jump silicon, which is 1.1 electron volts. If I'm a little bit less, I can jump, and I'm not quite having my best day at the pole vault match. Maybe I can only get up to germanium, which is 0.8 electron volts. And so, yeah, you can see. So then that's why we end up with this as our intrinsic carrier concentration. So this is temperature, 250, 300. This is the room temperature. We can see that the number of carriers that have ionized, that have jumped the band gap, are on the order of 2.5 times 10 to the 13 for germanium, because that's the lowest band gap of these three. Silicon is the middle one, right? Mama bear, Papa bear, baby bear. This is silicon. This is 1.1 electron volts, so it's got 1.5 times 10 to the 10. And keep that in context. That's kind of like 10 to the 10 out of the crystal, which I always like to kind of refer to as, think of it as on the order of Avogadro's number. So there's only 10 to the 10 out of something on the order of 10 to the 22, 10 to the 23, right? I think if you actually go back in the in your homework, I'm not sure if we had you calculate the density of silicon, but it's really on the order of 10 to the 22. So that's why I always pull this Avogadro's number as kind of for hand waving purposes. It's good enough. So you can see that I got 1 out of every 10 to the 13 silicon atoms has ionized one carrier. So it's still not a lot, but 10 to the 10 is, a fair number of carriers. Gallium arsenide would be 1.4 electron volts, supports the fewest number of carriers jumping the forbidden band gap. So then we talked about yeah, I guess that's good enough. So let me zoom this down a little bit. Oops. Yeah, there's temperature. So this is reciprocal temperature. So in other words, don't forget, this is cold, this is hot. So remember that donor ionized, just a few figures back, ionized at 50 K? So it really doesn't take much. Essentially, this is like 0 Kelvin. And at a modest amount of temperature, it ionizes. So probably room temperature is somewhere here. I guess it depends on which semiconductor I'm choosing. Is it silicon, germanium, or gallium arsenide? But maybe let's just say somewhere around here it's room temperature. So it's fully ionized long before it gets to room temperature, and it plateaus. So what it's inferring is that every donor has ionized, or every acceptor has ionized. That's kind of an ideal world. Sometimes donors and acceptors aren't that, don't fully work, or there's compensation and things like that. But generally, we're going to say that every one of them did what it's supposed to do. And here, if you remember, the story is that it's becoming intrinsic because this is when it's really getting hot, way above room temperature. And now I've got that carrier excitation of carriers going from the valence band to the conduction band. And the story was that I might have a few of these donors ionizing, but at this particular point, I got a lot of carriers doing the band-to-band. A lot of them, because it's really getting hot. And so maybe I got 10 to the 16 of the donors. But by then, maybe I've got 10 to the 17 of each of these holes and electrons. So now I've got 1.1 times 10 to the 17, and I've got 10 to the 17 here. And that's where I argue I'm going towards merging towards a 1-to-1 ratio of electrons and holes. I'm hoping this is showing up on the screen. And that's the definition of intrinsic. Intrinsic is when they're in 1-to-1 ratio. Drift, remember? Carriers are going to move. Once I have free carriers, they're going to move under the influence of an external electric field. So it's the number of them times the mobility. Mobility is centimeters squared per volt second. So if you do, I always stress units analysis. It really saved my bacon when I was an undergraduate. And so if you think about this, this is centimeters squared per volt second. So if I multiply by the number of carriers, and I multiply by electric field is volts per centimeter. So if this is centimeters squared per volt second, then I've got centimeters per second, right? Which is a velocity. And then I got the number of them. So I got a number of carriers times the charge Q. So I got how many coulombs are moving per centimeter, how many centimeters per second. So you can imagine how that's going to turn into a current. in this case a current density. And remember, I've always kind of humorously referred to drunkard's walk. This is basically the electric field, right? It's kind of moving around. The net effect is it might eventually get home after the basketball game tonight. Hopefully I didn't jinx it. But, eventually you get home. Here's the mobilities. These are key, actually. I was at this big conference for electron devices in San Francisco in December. And, a lot of the key innovation of devices is how to modify the materials so that we can squeeze more mobility out of them. Because it actually, once we get into field effect transistors, you're going to see how this is a key element. And drift and resistance, this is basically a definition of a wire and all this. And then temperature and mobility, I think I got a better diagram of that. So remember the argument about this is temperature on a log scale, and this is mobility, that's centimeter squared per volt second. So the argument here is there's two competing physical mechanisms. So be able to explain that. Again, now I think you've learned. My exams are looking at cause and effect relationships, the fundamental physical mechanisms that cause all this. So what's happening here is lattice scattering. Basically, this is your phonons, your heat. So as I suck the heat out, I have fewer phonons. The phonon population drops. So with fewer phonons, I don't have scattering. I don't have the electrons or the holes. I don't have them hitting phonons. Because phonons is like, so basically it's becoming frictionless. It's like I'm moving to outer space. I'm like Felix Baumgartner, right? So it's becoming frictionless. I'm getting less heat. So the mobility goes up. However, I'm still a carrier moving through a crystal. And that's what this is. So I still have, to get the carriers, I probably had to dope it. And so therefore, I've got those ionized donors that I've always kind of emphasized. Don't forget about the ionized donors, or don't forget about the ionized acceptors. So these are the impurities. And it turns out, though, that as it gets colder, you can imagine it moves more slowly, right? Yeah, think of right. You ever try to burn an ant with a magnifying glass, right? It's only moving so fast. When you get it a little hot, it moves a lot faster, right? And when it's cold, it's going to move more slowly. So here the carriers are moving more slowly. So therefore, when it goes past one of those ionized donors or acceptors, it's going very slowly past it. So you can imagine if you're going slowly past it, you're going to be scattered. You're going to interact with it more than if you zip right by. Right? If I'm gone, I hardly even notice that something brushed me as I went by. But if I'm going past slowly, I'm more likely to get tackled. Question?
So as the heat increases past that equilibrium point up there, the mobility slows down because of phonons?
Phonon population is being sucked out.
As we're going from left to right.
Yes, temperature.
So
Yes.
that means phonons increase left to right?
And the phonons are increasing. Yeah,
Okay.
it's getting hot.
Okay.
Phonons are quantized heat, so the hotter it gets, the more phonons. So that's what's going on here. It's just they're moving more slowly, so they're more influenced by scattering. In fact, here you can see, this is the conundrum that field effect transistors have, is that I need charge in my channel of my field effect transistor. We'll be getting to this in about 1 to 2 weeks. As I put more charge into the field effect transistor channel, I can carry more current, I can get more gain, I can get more output and all that. But to do that, in many cases, I had to put more doping into the system. And to put more doping into the system, I get, it slows everything down. As I put more doping in, I got more of that scattering, and my mobility drops. So the textbook, if you're looking at any of these textbooks we have on the reference ones or the one on record, they all probably have a table that show you nominally what the mobility of a semiconductor is, what the silicon is, the gallium arsenide and all that. In fact, actually, this is that table. this one. It says, the tables will say silicon is 1350. It'll say the holes are 480. You don't see that. Actually, you actually build a real device, and you're probably going to have to make a PN junction and dope it. So therefore, the silicon, which one's silicon? Silicon's this one. So if I dope it to something, you know, mid-range, 10 to the 16, 10 to the 17, my mobility is sagged because I have impurity scattering that's slowing things down. And if I dope it really highly to have that transistor move a lot of charge, my mobility really drops. And so then it becomes, you know, it's like the finish line gets farther away. The more doping I put in to make it better, the harder it gets to push the charge through because the mobility drops. And we'll talk about, and so Hall effect is nothing more than a way to use a magnetic field to induce a Hall voltage using the right-hand rule, and you get a modest amount of voltage induced between one side of your sample to the other side. I think there's a better visual that shows you the geometry of it. Yeah, here. So the right-hand rule, I put this semiconductor in the presence of a magnetic field, and if the current is going this way, right-hand rule, it causes a difference between this face and this face. If I have a voltmeter, a sensitive voltmeter, I'm going to measure a few millivolts, simply because the charge came in, and depending upon the whether it's holes or acceptors, the current's actually going to come in and bend, or the current's going to bend, depending on which carrier type, which is what induces the voltage difference. So I can measure that. So I can go into the lab and measure mobility, carrier concentration. Now, field effect, high field effects, is nothing more than our Felix Baumgartner argument, that the faster things go, right, the velocity, here's the electric field. It's like putting my foot on the gas pedal. The faster I go, I mean, the more I accelerate with the electric field, I'm going to linearly increase. But then friction of scattering with the lattice and everything is going to slow me down to the point that I'm going to hit my terminal velocity of a carrier going through. So the carriers don't go through at the speed of light. I hope you don't, if you ever say that, I don't want to go there. Don't ever think the carriers move at the speed of light. They're moving at 10 to the 7 centimeters per second. Optical absorption, we kind of talked about. Then once I have a band diagram, a band structure, exciting carriers, and so you can see how I can absorb a photon that's at the bandgap minimum, but I can actually absorb off axis larger energy photons. And so you can see the attenuation, I naught e to the minus alpha x. So alpha is representative of the attenuation coefficient, which I think I drew here, alpha, in inverse centimeters. And so basically, your semiconductor is a bandpass filter. So any photon that has an energy below the bandgap is transmitted. Any photon that is above the bandgap is going to induce an electron from the valence band to the conduction band, creating charge that can be measured if I built my device, my photodetector properly, and so it's absorbed. So it's a bandpass filter. And don't forget, I mentioned to you, windows, your window panes, your SiO2 window panes, has a band gap. It's just a very large band gap. So you go to the ultraviolet, it's going to absorb. But in the visible, what your human eye sees, it's transparent, because you're seen down here in the SiO2 spectrum. So here you can see I can actually absorb above the band gap, right? I can go to the higher reaches of the conduction band, and then it's going to rattle around like a pinball, and it's going to come down and thermalize and come to the minimum of the conduction band. And when I say thermalization, I'm using that word on purpose because it's often by shedding phonons, by shedding heat, that it relaxes down to the minimum. And that happens in like a picosecond. Yeah, here's the absorption. Yeah, we already covered this. Luminescence, that's just the other way. If I somehow put the carriers in and they fall back down, they're going to luminesce. You know, it's conservation of energy is essentially all it distills down to, is that the photon energy released is representative of the highest energy state minus the lowest energy state. So what's the energy difference at which it fell? It's not unlike throwing a ball up and going through a parabola, and I've converted kinetic energy at the bottom to potential energy at its apogee to kinetic energy when it hits the ground again a few seconds later. So back to bandgap. Carrier trapping. This is kind of what we're harping on about now a bit in our PN junction diodes. So this might be it's a good time to revisit, is I could have a trap. I could have a vacancy defect, interstitial, substitutional, some defect in my crystal lattice, which may manifest as an energy level within my forbidden bandgap. And you can see how this becomes a stepping stone for carriers to go back and forth. Remember, I may not have Usain Bolt kind of kinetic energy to jump the forbidden bandgap. Maybe I'm only the bronze medal winner, and I can jump to here, I can take a little rest, and then I can jump the rest of the way. So in other words, by having traps, it's like being, and I said this in yesterday's makeup video, it's like trying to cross a brook, and you don't want to get your feet wet, and the brook's too wide to jump across, but there's a few stones there, so you're just like stepping from the stones across the brook. These are stepping stones. They provide intermediary pause points. Now, everything's in play, I want you to know. This carrier can come up there, say, you know what, I'm kind of bored, I want to come back down. It could go this way, also, alternatively, and then continue on. I could have carriers that are up here, fall down. Basically, it is providing a connection pathway that is now connecting conduction band and valence band more succinctly. So this is why when I'm talking about carrier lifetime in PN junctions, this kills the carrier lifetime. Because now carriers have an easier way to go jump up and down. So this kills the carrier lifetime. Traps are usually a bad thing, and unless I want to make a very fast diode. So carrier lifetime, remember I've sometimes talked about, I can think of the world in a temporal sense, or a spatial sense, or an energy sense. This is lifetime, so I'm just talking about the carrier lifetime, about when I create an electron hole, how long does it stick around before it recombines, this tau. How many tau seconds before it falls down and relaxes. And yeah, so this is kind of, this is time in nanoseconds. So this is showing you, perhaps I shot a laser beam on my semiconductor and I created 10 to the 14 holes, no, electrons, and it's normally p-type, which jumps from 10 to the 15, and then I get a little bump up because I got 10 to the 14 holes as well. So I did 10 to the 14 photons, got dumped into this. It created 10 to the 14 extra electrons, 10 to the 14 extra holes, which is added to the original hole concentration, which is 10 to the 15. So I got 1.1 up here, and I got 0.1 down here, 10 to the 15. But over time, equilibrium's restored, right? This is the analogy of getting the flu shot and how you get a concentration of serum, and it's a concentration, but as time comes, it recombination and everything, and it goes back to its equilibrium point, and it's distributed. Fermi level, I guess I gotta turn sideways, sorry about that. Some of that. Diffusion, right? Carriers. So if you actually put it all together, adding drift and the electric field, these are the current equations. The two major current components are the electric field driven, which we talked about drift, and the other one is diffusion current. So holes and electrons, right? That's when we talk about p-n junctions. They're moving from one side to the other by the concentration gradient that drives it. So you have the concentration gradient dn dx is a function of distance, and the diffusion coefficient tells you just how fast they move. And yeah, so they spread out over time. And yeah, so the electric field essentially really causes band bending. Electrons go down, holes go up. And here you can see the Einstein relation, which actually is a way that the diffusion and the drift, which is predicated on mobility, are actually intertwined with each other. And a lot of those Java applets, I really apologize, but I have no jurisdiction over them. I tried to show a few times Java applets, and I put the link at SUNY Buffalo on the Carmen webpage. They have a really nice experiment, at least they used to, called the Haynes-Shockley experiment. And no, I did show that a little bit, I guess. That one was one of the few that worked. And it shows you how diffusion and drift are actually sort of variations on the same thing. And the Einstein relation shows you that it's a constant. And yeah, that's kind of petering out. Yeah, the Haynes-Shockley experiment. Yeah, so you put a pulse of light in, and if I have an electric field, the pulse is going to move down the bar. But so the electric field makes the pulse move down the bar. The diffusion causes the pulse to broaden. And through the Einstein relation, they're actually different interpretations of the same thing. We didn't get into packaging. I didn't have time for all that, so skip that. And okay, I think that's one we just did, wasn't it? Yeah, that's one we just did. And then that we already did that. That's the one pager. Didn't we already do that? Yeah, we already did that. So then we're into p-n junction formation. And this actually I threw into midterm 1, how to form a p-n junction. We kind of talked about some of the crystallographic. I kind of exposed you. I could do alloying. I could do liquid phase diffusion. That's diffusion. Yeah, you calculated diffusion, stick it in a tube furnace. I could do ion implantation. That's in midterm 1, so I'm not going to be late. I'm going to jump past this. I could do these epitaxes. These are the epitaxes. CVD, MOCVD, MBE. These are all ways to epitaxially grow these layers. There's an MBE reactor. And so the p-n junction formation is the last thing I'm going to talk about, and then I'm going to open up for questions. The p-n junction formation is really critical. It's a fundamental about how to make it, because a slab of P or a slab of N doesn't do anything. A p-n junction allows me to start to build the framework of something interesting. And why does a p-n junction behave the way it is? Well, it's because I put P and N next to each other, because they have dissimilar electron and hole concentrations. And so Mother Nature wants to move towards equilibrium. I keep liking the analogy of the Panama Canal or something like that, where I have high water on one side, low water on the other, and I open up the lock, and what happens? The water levels equilibrate, right? That's what's happening here. I have high electron concentration, I got low electron concentration. Here's holes, high concentration, low hole concentration. High electron concentration, low electron concentration. So I open up the floodgates. So somehow in my Gedanken experiment, I have magically stitched this P and this N together. You saw how I could do that. I could epitaxially grow. I could deposit a layer of atoms at a time, and I could epitaxially grow anything I want. And in fact, one of the Denman, I told you I just came from the Denman. One of my teams they're growing graphene in our laboratory, which by the way is right here. If you want to see graphene, it's actually this carbon electronics. Actually, we talk about our semiconductors as being sp3 hybridized. This is carbon and sp2 hybridization. And it actually grows as little benzene rings fused together. And it's actually a single monolayer of atoms stitched together in this mosaic pattern. And that is a semiconductor. And I have a team of undergrads synthesizing that in a lab upstairs. So where did I go? Oh yeah. So as I open up the floodgates and I epitaxially grow this or whatever, or I did a diffusion, then obviously the holes go from high concentration to low. The electrons go from high concentration to low. So those are the free electrons and the free holes diffusing. But as they diffuse, they're revealing the ionized donors. They're revealing the ionized acceptors, which have a positive charge and a negative charge. And they're fixed in their location. Because the phosphorus atom that created this plus one charge, each one of those, is housed in the crystal lattice, bound by 4 covalent bonds to 4 adjacent silicon atoms. So unless I heat, as long as this is at room temperature, that phosphorus atom is not going to move anywhere. That phosphorus atom only moved when I did the diffusion, like the first computer problem. And remember, that only moved at what was some of the temperatures you guys used? 900? Yeah. So, it's not going to move at 300. And I had to take it up to 900 to get that phosphorus. So the phosphorus is immobile. It's tethered by 4 covalent bonds to 4 silicons. And so the ionized donors are spatially separated throughout, forming our magical depletion region. So I have a constant doping of the ionized donors, constant background of the ionized acceptors, because it's uniformly doped in this simplified experiment. And you've hopefully learned about Gauss's law in physics. So Gauss's law is you integrate the charge to generate electric field. So constant charge means linearly varying electric field with the maximum electric field at the metallurgical junction, because every electric field line is crossing that boundary, and the electric field lines are terminating on the charges. So as it goes deeper and deeper, more and more of the electric field lines are truncated, terminated, and so they finally extinguish by the time you get to the edge of the depletion region when you run out of charge. And this other book takes it a little bit farther. It shows that you take Gauss's law and integrate the charge, you get electric field, but integrate it one more time and you get potential difference. Potential difference is the origin of the band bending. So going back to the Panama Canal, open up the lock, the waters equilibrate, the bands bend, goes like that, Fermi level aligns, that's my watermark level of my electrons, and it aligns what the conduction band and valence bands are bending accordingly. And so the argument is the carriers, due to the population difference, free carriers diffuse, and after they diffuse, they reveal ionized donors and acceptors, which then starts to open up and establish an electric field. The electric field is causing the band bending, which is now starting to oppose diffusion because I'm establishing an energy barrier. And eventually the establishment of the electric field inhibits further diffusion, and eventually I establish equilibrium where drift and diffusion are now net zero. And that's my equilibrium, and that's where the story ends for midterm 2. Questions? Yes?
I have a question in the indirect band gap. So, the phonons help the electron to reach the point where it just goes down, right?
Yeah. In some sense, you can think of it as phonon, you can actually think of it as a phonon being absorbed or phonon being emitted. You could actually go, it's just a vectorial analysis. So I could actually have a photon that's of this energy where I am releasing a phonon, or I could be absorbing a phonon, and then I'm going to have a higher energy photon. But it's just a vectorial analysis established through the energy momentum band diagram, band structure diagram. Yeah. Both are possible. This is an absorption, absorb phonon, and this is release phonon.
Established because of the...
Well, you're always going to have, phonons is heat. And most of our semiconductor devices are operating ostensibly at room temperature. So you're always going to have heat, so you're always going to have some phonons. It's only when I'm doing a low temperature study, physics experiment, and I'm dunking it in liquid helium that the phonons disappear. And even then, I can still release a phonon, I just can't absorb a phonon. Yes?
In intrinsic, extrinsic, and ionization graph, the dotted line that follows the intrinsic, what's that?
Oh, that's just an asymptote. I'm not sure I can find that quickly. Let me try. That one? No, it's not going to be in that one. So. A 4C 4. That's just an asymptote showing you the intrinsic. So the intrinsic carrier concentration is just, yeah. Yes.
I have a question relating to the energy diagram that relates to the Bandgap, how it forms, how it looks like a parabola, but there's it's missing parts or allowed energy states. I don't really get how that happens.
I've heard it once said that quantum mechanics doesn't make any sense the first time you hear it. But you're supposed to believe it because your professor says so. And the second time you hear quantum mechanics, you still don't quite understand it, but your professor says so again, and so you start to, and maybe by the third time you see it, you actually start to acquiesce and accept it. So, as a wave, the electrons are moving as a plane wave. So think in the simplistic sense, sine and cosine, a series of sines and cosines. And I have a periodic crystal through which those plane waves are moving. So I have a series, a linear superposition of atoms, creating a linear crystal. So instead of a three-dimensional crystal, we'll make a linear crystal. And therefore, a plane wave of electrons moving through that, right? You can imagine that a wave going through the crystal, that is a nice harmonic fit. This is a nice Fourier rendering that this Fourier component would probably be represented within that crystal. But if I take another plane wave and it's some detuned where it's asynchronous to this, you can imagine that the interference of the plane wave and the linear crystal is going to destructively interfere with it, and it's going to be attenuated. In other words, that plane wave is not supported to propagate through the crystal.
So
Therefore, certain plane waves are not supported, and others are.
So certain frequencies of waves are allowed, but what about them not being in phase when they interact with the crystal?
Right. That's what it is. That's the Fourier. If you do a Fourier expansion of an arbitrary function, you'll see that some of them are allowed, and there's certain eigenvalues that are supported, and some that are not. Question? Clear as mud? Very good. Good. Okay, mull that over. There's many books are on reference at the library. Each of them have their pros and their cons. One of them doesn't float your boat. Look at some of the others. Hopefully you can find them. I think each is supposed to nominally have a 2-hour checkout window, so hopefully no one squats on any of them. And so, good luck.